Hello and welcome back to Edu-Malanga. Today we're continuing with the lesson, the sum of geometric series, but we're looking at a new concept under this lesson, and that is sum to infinity of certain kinds of geometric series. The sum of geometric series is the fourth lesson under the first unit of the year, which is patterns, sequences, and series. And today we're going to introduce and understand the kinds of geometric series that you need in order to sum to infinity. So let's get started. From everything that I've explained, we understand that you can sum an infinite number of terms, which is basically n tending to infinity, for certain kinds of geometric series. And what we will do today is understand and expand on exactly what kind of geometric series you can sum to infinity. You can sum a geometric series to infinity when -1 is less than r and r is less than 1. So r, remember, r is our common ratio for the geometric series, and when your r is less than 1 or greater than -1, then you can sum the terms of that geometric series to infinity. To explain why this works like this, I'll start by introducing a concept, and then I'm going to explain the concept further. And the concept we're going to look at today is converge versus diverge. When things are converging, they're tending towards one thing. So if I was to use a diagram, for example, I would say we start off with a group of things, and what happens is they converge and work towards the one particular thing. That's when you have convergence. Versus when you have divergence, what happens is you start off with a group of things and they seem to tend to grow as you're going as well. So they're opening up, they're getting bigger and bigger, they're not tending to one particular thing, and that's when you have divergence. So let's start by looking at divergence, and we're going to rule out the series that diverge. Then we're going to look at the kinds of geometric series that converge, and we're going to come up with a formula for calculating the sum to infinity when your series are converging. Say we have a geometric series, for example. Our geometric series has r is equal to the power 3 and a is equal to 3. So how will the equation for that geometric series look? Remember, the equation for a geometric sequence is what we use, and that equation looks like this. You have Tn is equal to a times r to the power of n minus 1. So for the series where r is 3 and a is 3, we're going to have 3 times 3 to the power of n minus 1. If you remember from grade 11, the laws of exponents are that when you have two exponents and you're multiplying things with the same base, you add the exponents. So this is 3, it's essentially 3 to the power of 1. And what the equation will then become, it'll be 3 to the power of n, because you have n minus 1 plus 1. So the equation for this series will be that Tn is equal to 3 to the power of n. Let's look at this series and get started with it. When you turn this into a series, you will have Sn is equal to 3 plus 3 to the power of 2, that will be 9, plus 3 to the power of 3, 27, plus, and you'll keep going on and on. What's happening in this series is that the numbers are getting bigger as you are growing. So what happens is when your n turns to infinity, which means your n is growing, here your n was 1, 2, 3. What happens is also the term number, which is the number that you end up with, like 27, 9, and 3, and so forth, is also tending to infinity. So what's happening with this kind of series is that you have divergence. It is diverging. Let's continue to look at another series that will diverge as well, and that series will occur when we have Tn is equal to -3 to the power of n. So it's similar to the first one, except now we have a negative in front. Let's get started and write down the series that would come from this equation. Again, it will be Sn is equal to -3 to the power of 1, that'll be -3. -3 squared, that will be plus now 9. -3 to the power of 3, that will be minus again 27, and it will have a plus and it will keep on going. So again, if we look, when our n tends to infinity, so as our n is growing, what we have is that our series term number, which is also growing as well, it's tending to infinity, so we also still have divergence. But let's also note that we have a minus, plus, minus. And what we call this behavior in a geometric series, when your series jumps from negative to positive back to negative, we call it oscillating, which means it's jumping back and forth between the negative and the positive. So this one we can describe as diverging and oscillating. If we try to add the terms of a series that's diverging, so our Tn is tending to infinity on its own. Now if we were to try and add for a series Sn, we're going to have infinity plus infinity at the end, and we're not actually going to have a number. So that's why when your series is diverging, you cannot add the terms to infinity because they are equal to infinity themselves anyway. Now let's move on and look at a series that is converging. You get a series that is converging when you have the common ratio between -1 and +1. And let's start by looking at an example where our common ratio is 1/3. R is equal to 1/3. We'll look at a series again, which basically has Tn is equal to 1/3 to the power of n, meaning that our first term A is also equal to 1/3. Let's write down the terms of this series now. We have that Sn is equal to the first term 1/3 to the power of 1, that'll be 1/3, okay, plus the second term 1/3. Let me put brackets here so we know that the power goes into everything. 1/3 to the power of 2, that will be 1/9 because that's 1/3 squared, okay. Then we go to plus 1/3 to the power of 3, that's 1/27. If we notice what's happening here as we keep increasing, so as our n is tending to infinity, what's happening with our terms? Our term numbers are getting smaller and smaller, so they're tending towards 0 actually. 1/27 is much smaller than 1/3. So what's happening here is that our series is converging towards the number 0. Let's continue and look at a series where we have that Tn is equal to -1/3 now, close our brackets, to the power of n. Again, let's write down the series that would result from this. We will get that Sn is equal to our first term, -1/3 to the power of 1. That'll be -1/3 as it is. -1/3 squared now will give us a positive 1/9, okay. And then -1/3 to the power of 3 will go back to being negative and it'll be 1/27 plus, and it'll keep going from there. Again, what we can see is that as our n tends to infinity, so as our n is growing, we have our term numbers. They're tending towards smaller numbers as well, towards 0 again. And we still also have oscillation, so it's still oscillating. So now that we understand convergence and divergence, let's say exactly when does a series converge? A series, a geometric series, yes, let's say that, converges when r is greater than -1 and r is less than 1, and the terms tend towards 0 as n increases. So this is when you have a converging geometric series. You can sum the terms to infinity of a geometric series that's converging because it's converging towards a single term. Let's come up with a formula for calculating the sum to infinity of a geometric series that is converging. It has to be converging, guys. If you see a question that's asking you to sum to infinity, the first thing that you have to check is that, is the series converging? And what will you do? You will look at the r. Is it a number between -1 and 1? Let's come up with the formula. If we remember, when we did the sum of geometric series, we derived two formulae that we used to sum the terms of a geometric series. I'll write them down. We had that Sn is equal to a times open brackets r to the power of n minus 1, close our brackets, divided by r minus 1, and the other formula was a times open the brackets, 1 minus r to the power of n, close the brackets, 1 minus r. If we remember, I've always said that when our r is a fraction, so r is equal to, for example, 1/3, we should try and use this formula because it becomes easier to say 1 minus a fraction, and when you power a fraction it gets smaller. So we're going to work with this formula to sum the terms to infinity of our geometric series. So let me rewrite it. We're going to have that Sn is equal to a times open brackets 1 minus r to the power of n, close our brackets, all over 1 minus r. So our n is going to start tending to infinity now. So let's say n is equal to infinity. This equation will then become s sum to infinity, yes, is equal to a times open brackets 1 minus r to the power of infinity divided by 1 minus r. Let's remember, we said our r was a fraction, which means it's a number, for example 1/3, and we said what happens is, as our n tends to infinity for that kind of series, the number gets smaller and smaller and smaller and tends to 0. So we're then going to have a times open brackets 1 minus 0, because at infinity, when we have 1/3 to the power of infinity, we're going to get a 0, divided by 1 minus r. And what happens 1 minus 0? You simply get 1, okay? So in the end, then we have that sum to infinity. When you're summing an infinite number of terms, it's equal to a divided by 1 minus r. That's a very simple formula, right, guys? I hope you'll be able to remember it. And I also hope you understand what I mean when I say the terms, as n is increasing, the terms are tending to 0. We can see it over here as well. So maybe I should just do like a quick show when we're looking at this one. Say for example, we say n is equal to 500. Quickly put it in your calculator. You're going to have 1 over 3 to the power of 500, and that's equal to 0. Your calculator will return a 0. So as your n is increasing, your series is tending towards 0. I hope you understand very clearly. Thank you very much for joining us for this video. Join us again in the next one. I'm going to do 2 examples on the sum to infinity of a geometric series.